Hello, and welcome to The Complete History of Science. Series 7, Episode 4, Tycho's World System. The Great Comet of 1577 caused excitement and fear across Europe. At the time, astrology was widely practiced, not just by the general public, but by astronomers themselves. Comets were seen as omens, signs of divine warning or impending disaster. Jørgen Dybvad, a professor at the University of Copenhagen, published a pamphlet on the comet filled with astrological predictions. Dybvad declared that the day of the Lord was at hand and warned of war, pestilence, and religious upheaval. Tycho Brahe, though, had cooled on astrology. Although he still believed that celestial bodies could influence human affairs, he had grown skeptical of astrology's predictive power. He was far more interested in the comet itself. Through his work, Tycho had reached a surprising conclusion. The comet was orbiting the Sun. The contrast between Tycho's work and that of other astronomers at the time was enormous. Across Europe, he was alone in taking measurements with any kind of regularity. From his specialized observatory, he took measurements with unprecedented precision. Yet, in the late 1570s, Tycho remained dissatisfied with the accuracy of his instruments. He returned to his workshop to build bigger and better ones. He produced several large quadrants and a new armillary sphere. By 1581, he claimed he could achieve a resolution of 4 arc minutes, and by 1583, a single minute of arc. The downside was that the size of his instruments meant that they were increasingly difficult to use alone. One of his quadrants was 2.5 meters in diameter and required at least 2 or 3 able-bodied men to operate. Tycho would need assistance throughout his time on Ven. By this point, at least 8 different assistants had worked with him, though most had stayed only briefly. Life on the cold, wet island, taking meticulous nightly measurements, was not for everyone. Tycho could also be difficult. A noble by birth and temperament, he was often overbearing, treating his assistants more as hired help than as colleagues. Even so, he managed to retain a few long-term collaborators. Peter Flemloes remained with him, and 2 more assistants joined, Gellius Saskarides and Elias Olsson. Saskarides was a clever and quick-witted Dutchman who was the son of a Hebrew professor in the University of Copenhagen. He stayed for most of the decade before leaving to pursue medicine. But Tycho's most trusted assistant during this period was Olsson. Unlike the others, Olsson shared Tycho's passion for astronomy and was entrusted with making key measurements when Tycho was unavailable. By the 1580s, Tycho was equipped with all of the instruments and assistants he needed. Up to this point, he had made observations irregularly, as and when required. But now, the advantages of life on Ven had come to fruition, and he began a regular program of observations. Most observation took place during the early evening, on the dark and cold months between September and March. The unprecedented accuracy of these observations soon led to an interesting problem. The first measurement Tycho ever took on Ven was of the winter solstice. He used this to calculate the island's latitude, which he found to be 55 degrees and 50 minutes north of the equator. But there was another method for determining latitude, by measuring the angle of the pole star. Using this second method, Tycho arrived at a slightly greater value. The discrepancy was small, only about 4 minutes of arc, where 1 minute again is 1/60th of a degree. Prior to Tycho, such differences would have gone unnoticed. They fell within the expected margin of error. But Tycho had confidence in the precision of his instruments and believed the discrepancy was real and significant. By reflecting on the problem, he identified the likely cause: refraction. Refraction is the bending of light as it moves between different materials. For example, when you look into a clear pool, objects beneath the surface appear displaced. This is because the light changes direction as it passes from air into water. Something similar happens as light enters through the atmosphere. The further away from Earth you are, the less dense the air, and this changing density causes light to bend. The idea that celestial light could be refracted in the atmosphere wasn't new. Ptolemy had written about the problem 1,000 years earlier. But while he understood that refraction occurred, he had no reliable method to measure or correct for it. Tycho likewise had no way of knowing how much refraction would bend the light. He only knew that light which passed through the atmosphere at a more oblique angle would bend more than light coming from directly above. Based on this, he reasoned that the latitude measurement from the pole star was much more accurate than the figure from the solstice. This is because, at the solstice, the sun is low in the sky and will experience greater refraction. The pole star, by contrast, is higher, meaning it will experience less refraction. This detail immediately set off alarm bells in Tycho's mind. He realized that atmospheric refraction could have introduced significant errors into earlier astronomical measurements. He was especially concerned that Copernicus's value for latitude might have been inaccurate, and that as a result, his calculations of fundamental astronomical constants would also be affected. In particular, Tycho was concerned that Copernicus's value for the obliquity of the ecliptic was wrong. There are two ways to understand the obliquity of the ecliptic, depending on whether you adopt a heliocentric or geocentric perspective. In a heliocentric model, the obliquity represents the tilt of the Earth's axis relative to the plane of its orbit around the Sun. In a geocentric model, the obliquity represents the angle at which the Sun appears to orbit the Earth relative to the equator. Regardless of which perspective we adopt, the obliquity was a key quantity for Tycho. In order to check Copernicus's measurement, Tycho dispatched Elias Olsson to Frombork. Traditionally, the obliquity of the ecliptic was calculated using two measurements: the angle of the Sun above the horizon at the winter and summer solstice. But Tycho had realized that the winter solstice was most affected by refraction, so he attempted to eliminate this measurement from his calculations. Instead, he used the angle at the summer solstice and a measure of the angle to the pole star. This gave a higher value than Copernicus, 23 degrees and 31 minutes. Tycho was very proud of having achieved a new value for such a fundamental constant. During this period, Tycho kept up his correspondence with Wilhelm, and together they noticed another strange, related effect. The increased accuracy of clocks in the 16th century had opened up new possibilities in astronomy. Wilhelm, like Tycho, was the proud owner of a mechanical clock, but he had noticed something strange. When he tried to predict the time of sunrise, it didn't match what his clock was telling him. The sun seemed to rise a few minutes earlier than it should have. Tycho quickly realized the cause was once again refraction. The bending of light in the atmosphere made the sun appear above the horizon, even though in reality it was still below. The more he thought about it, the more troubling refraction became. If it could shift the apparent position of celestial objects, then it could affect all kinds of astronomical measurements. Tycho decided to study refraction properly, not just in principle, but quantitatively. He wasn't the first to try. The method he used was based on earlier work by Al-Haytham. It involved measuring the sun's position on the solstice from sunrise to sunset, and tracking how its position shifted over the course of a day. From these measurements, he began building a table of values showing how much refraction occurred at different angles in the sky. But the work had serious flaws. Firstly, Tycho assumed that refraction could be ignored entirely for observations above 45 degrees. This was wrong. He also believed that light from different celestial bodies, the sun, moon, planets and stars, would refract by different amounts, and so he made separate tables for each. But his greatest mistake was trusting Ptolemy's value for solar parallax, 3 minutes of arc, a number that was far too high. Rather than estimating the value himself, he took Ptolemy at his word. This would have lasting implications for the accuracy of Tycho's work. The irony was that in Tycho's striving for precision, he ended up with less accurate results. Copernicus's measure of the obliquity, without taking account of refraction, had in fact been closer to the true value of 23 degrees and 29 minutes. No matter, Tycho pushed on with his measurements. He had his sights on a much greater prize than refining a single constant. Since his lectures in Copenhagen, Tycho had been considering the problems raised by Copernicanism. He understood that Copernicus's theory was a major improvement over Ptolemy's. In particular, it had resolved one of the long-standing criticisms of Ptolemy's model, a device called the equant. Since the time of Alhaitham, astronomers had disliked the equant because it violated the principle of uniform circular motion. The equant was an off-center point around which a planet would appear to move at a constant speed, a kind of mathematical fix to make the model work. Many astronomers in the 16th century still rejected heliocentrism, but they almost all admired that Copernicus had done away with the equant entirely. Another benefit of Copernicus's theory was it explained retrograde motion, the strange phenomena which makes planets appear to reverse direction in the sky. If you watch a planet night after night, it usually moves from west to east, but every so often it seems to pause and then move from east to west for a short while before returning to its original path. Ptolemy explained retrograde motion using epicycles, small circular orbits which moved on larger ones. The system worked, but it was clearly a mathematical fix rather than a physical explanation. Copernicus offered something simpler. If the Earth and the planets are all moving around in their own orbits, retrograde motion happens naturally. It's just a matter of perspective. Imagine driving on a motorway. When you overtake a slower car in the next lane, it seems, just for a moment, to move backwards. However, despite these advantages, Tycho could not abide the most striking aspect of Copernicus's theory, the moving Earth. Tycho decided there had to be an alternative, a model that kept the benefits of Copernicus's theory while leaving the Earth unmoved. Over the course of the 1580s, he developed a system of his own. He placed the Earth at the centre, with the Sun orbiting around it, much like in the Ptolemaic model. But instead of having all the planets orbit the Earth, Venus and Mercury orbited the Sun. This idea had a precedent. It resembled a system described in the 6th century by Martianus Capella. Part of the credit also belongs to a mathematician called Paul Wittig. Paul Wittig played an important role in helping Tycho shape his geo-heliocentric system. Tycho, in return, showed Wittig his instruments, data, and observatory. During his visit to Venn in 1580, Wittig introduced Tycho to mathematical tools, including the law of cosines, and likely shared ideas about placing Mercury and Venus in orbit around the Sun, while keeping the Earth fixed at the centre. Unfortunately, the relationship between the two men soured slightly in the aftermath of this meeting. After leaving Venn, Wittig travelled to visit Wilhelm, Landgrave of Hesse, and showed him several of Tycho's instrument designs and observational data. Wilhelm was impressed and awarded Wittig a gold chain. When Tycho learned of this, he sent his assistant Peter Flamlows to Hesse to make it clear that the designs and the data were his own. The incident marked a turning point for Tycho. From that point on, Tycho began to guard his results more closely. He also recognized something else. As talented as Wittig was, he lacked Tycho's instruments, his assistants, and his observational skill. Theoretical models that Tycho was developing would mean little without the data to test them. And in Europe, no one else had the data. Tycho continued to work on his model and soon made a major breakthrough. Reflecting on the Great Comet of 1577, he was now certain that it orbited the Sun. But when he charted its path, he noticed something else that was surprising. It seemed to pass through the orbits of Mercury and Venus. For many astronomers in the 16th century, this would have been hard to accept. At the time, it was widely believed that the planets were carried on solid celestial spheres. Picture the planets being embedded in large glass balls which rotate around the Earth. The idea was inherited from late Islamic astronomers who had insisted that astronomical models should reflect real physical structures. If the spheres were solid, then comets couldn't pass through them. But Tycho's observations showed otherwise. The comet's path cut across the supposedly solid spheres. This insight opened up Tycho's thinking. Until then, he had placed only Mercury and Venus in orbit around the Sun, while the outer planets still orbited the Earth. He knew that if the outer planets orbited the Sun, their paths would cross with the Sun's own orbit around the Earth. But if he gave up on the idea of solid spheres, he could try a more ambitious system. In his new model, all of the planets orbited the Sun, which in turn orbited the Earth. When exactly Tycho revised his view isn't known, but by the 1580s he was actively looking for data to support a more radical version of his system, one in which all of the planets orbited the Sun, while the Sun continued to orbit the Earth. One of the challenges was working out exactly what kind of evidence would support this idea. Tycho understood it was difficult to distinguish between competing models using observations alone. This had been a problem for Copernicus as well. Copernicus had good reasons for believing in the heliocentric system, but the evidence, such as retrograde motion, was circumstantial rather than definitive. From a geometric standpoint, the models were very similar. Whether you placed the Earth at the centre or the Sun, you could still produce roughly the same predictions. The difference was in the interpretation, not the math. Tycho, however, did have one idea how he could differentiate between the Copernican and Ptolemaic models. He would again look for parallax. Parallax had been the great weapon in Tycho's arsenal, and was the key to his analysis of the new star and the Great Comet. Here, though, he would put parallax to a new use. In the Copernican model, the distance between the Earth and the planets changes over the course of the year, as each planet moves along its orbit around the Sun. By contrast, in the Ptolemaic model, where the planets orbit the Earth, the distance to the planets remains roughly constant. Tycho's idea was to look for parallax in the positions of the planets. If the Copernican model were right, then Mars, at certain points, should come very close to Earth, even closer than the Sun. Tycho believed that that kind of proximity would produce a measurable parallax, something that would never occur in the Ptolemaic system. Tycho used his best instruments in the search for Mars's parallax. To have a chance of detecting it, he needed to observe the planets when they came closest to Earth, a point that occurred roughly every 2 years. His first attempt, at the start of 1583, produced a null result. When he tried again in 1585, the outcome was even more frustrating. The parallax appeared to be negative, that is, the shift went in the opposite direction to what he expected. Tycho began to suspect that refraction was distorting his results. But by 1587, his observatory was running at full capacity. His most precise instruments were installed and he had a full team of assistants on hand. He wrote to Wilhelm of Hesse expressing his confidence that this time he would detect the parallax. On the night of March 10th, Tycho carried out the observations himself. The records from that night are written in his own hand. He analysed the data carefully, this time correcting for atmospheric refraction. The final figure he arrived at for parallax was 5 3/4 minutes of arc, implying that Mars had come very close to Earth. For a time, Tycho allowed himself to hope quietly he might have found the evidence which would overturn the Ptolemaic system. Of course, Tycho had no intention of replacing Ptolemy with a purely Copernican system. Instead, he would argue for his own model, one that preserved the strengths of Copernicus but kept the Earth stationary at the centre. Tycho assumed, probably with good reason, that other astronomers would accept this compromise. To him, it seemed like the best of both worlds. The credit for Tycho's system, however, came under threat almost immediately. In 1584, he received an unexpected visitor, a man named Nicholas Reimers Barr, but better known as Ursus. Ursus was of low birth, but had risen through intelligence and ambition. After attending university, he had written a successful Latin grammar and another book on surveying. He would have seemed a prime candidate to become one of Tycho's assistants. Ursus's arrival seemed promising. He came in the company of Eric Lang, a nobleman and friend of Tycho, and he even composed a poem on arrival, thanking Tycho for his hospitality. But the relationship quickly went south. There was something about the young man that Tycho disliked. Ursus was too presumptuous, too self-assured, perhaps not deferential enough for Tycho's taste. Tycho was, after all, a nobleman, and one of the most respected astronomers in Europe. Slowly, Tycho became distrustful. He was still wary of visitors after the incident with Wittig years earlier, and Ursus began to raise similar concerns. Growing increasingly uneasy, Tycho started to exclude him from conversations with Lang. While Tycho was entertaining his guest, Ursus took to lingering in the library. One day, he was caught going through Tycho's papers. As a result, Ursus was moved to different quarters, where he could be more easily watched. A few days later, Ursus was found with notes he had copied from Tycho's work. When confronted, he began screaming uncontrollably and couldn't be calmed down. Tycho and Lang tried to smooth things over by treating the episode lightly, almost as a joke, but the damage was done. Ursus left, and for a while, Tycho heard nothing more about him. Then, 2 years later, he reappeared at the court of Wilhelm of Hesse. There, he claimed to have invented a new astronomical system, one that looked remarkably similar to the model Tycho had been developing. 4 years after that, Ursus published his version of the system. But it had serious flaws. Flaws that any careful observer, and certainly Tycho, would have spotted immediately. Most notably, Ursus's model did not allow the orbit of Mars to intersect with the orbit of the Sun. It's likely Ursus still held the idea that the planets were carried on solid celestial spheres which couldn't overlap. The problem was, by forcing the orbits to stay separate, Ursus's model could no longer match the data. It might have looked plausible on paper, but it would never account for actual observations. Regardless, Ursus's publication pushed Tycho to act. He had already written a long manuscript on the comet of 1577, detailing its path and his parallax measurements. He now added an extra chapter that outlined his own geo-heliocentric system. In it, Tycho presented his model formally for the first time. He included the results of his parallax observations of Mars as direct evidence in support of his approach. Tycho's model was far more sophisticated than the one published by Ursus, but it still contained a flaw. When he published his work in 1588, he believed he had measured the parallax of Mars the year before. In reality, he had made several fundamental errors. The problems were familiar ones. He estimated Mars's parallax should be around 5 arc-minutes, but he based this on Ptolemy's outdated figure of 3 arc-minutes for the parallax of the Sun. Ptolemy's estimate was far too high, and therefore so was Tycho's. The only reason Tycho believed he had detected parallax was because of his inaccurate accounting for refraction. In truth, the parallax of Mars was far too small for Tycho to measure, especially given the limitations of his instruments and his inability to fully correct for atmospheric refraction. To his credit, Tycho later recognized the mistake and retracted his claim. He still believed in his system, but he knew he had no direct evidence to support it. Every 2 years, when Mars came closest to Earth, he again tried to measure its parallax, but he never succeeded. At the same time, his resentment towards Ursus only grew. Tycho poured huge amounts of energy into trying to undermine Ursus's reputation and discredit his work. Tycho Brahe had built one of the most precise observatories in Europe, created a new model of the cosmos, and measured the heavens with unmatched care. But the one thing he needed most still eluded him: proof. Over the years, Tycho became increasingly frustrated at his inability to demonstrate his system was the correct one. He needed help, and he found it in a young German mathematics teacher, Johannes Kepler. Ultimately, it was Kepler who would overturn Ptolemy and invent a new astronomy. I'll return with that story later in the year. I'll also release a short update soon to discuss the health of the show and what you can expect. But for now, goodbye and keep watching the skies.